Okay, so let's move on with our discussion. And in the last class, we discussed the construction of a master-slave flip-flop, right? Using two latches in order to get a positive edge triggered flop. We said you needed two right? So clock, we needed a negative latch first, which means that this has to be 0, this has to be 1, D can go out to QM, right? This is my latch L1, and then we have another mux here, and Q, and this is what, again this is clock, and then I'm going to call this 0, 1, right? So this is L2, this is a negative latch, this is a positive latch, okay? So the key idea was data that you sample on the positive edge should be held for the entire period of the clock. So it is being held in two steps. The first half data is being held by the L1, where L2 is transparent. Second half, L2 is opaque and it is holding the data, and L1 becomes transparent. Okay, this is how we analyze this. We looked at the timing diagram of how a change in the data, even after the rising edge, after the sampling edge, data can go through till QM, the first output, but cannot go beyond that because L2 is then opaque, right? So you have to get used to this timing diagrams and also analyzing which latch is opaque or transparent. Okay, that's very key to analyzing all the other timing constraints also, which we will discuss going forward, right? Then we started looking at a particular circuit implementation of this flop, okay, and we said that let me call this, so this is D and clock equal to 1, it has to go through, right? So no, clock equal to 0 it has to go through, right? That's basically a negative latch. Clock equal to 0, clock, and we constructed another gate like this, clock bar. Okay, and then we said that you cannot just have transmission gates, because in order, if I asked you the question saying, suppose I had a, let me just explain that once more because there was a question last time, right? We connect this like this, QM and D. Suppose I asked you the question, what is the delay of this flop, setup time, or what is the C to Q delay, right? Then you will ask me another question saying, what is driving this flop? Because right now there is no path to VDD or ground for this flop on both sides, right? On the D side as well as the feedback side. So there is no way that I can tell you the delay or characterize this flop. What does characterization mean? It means that as a standard cell designer, I design a gate or a flop, and then in your assignment now, you are characterizing the delay of a adder against the loads, against the slew. What are you doing? You're basically saying if the load is this much and the delay is this number, I should be able to give you that number. That is what is known as characterization, right? Here, when I try to characterize, I need to know where this flop has been placed. Without that, I cannot tell you, and therefore I cannot design a standard cell element like this. Some special places you are free to go and place this, circuit as it is and you get it to work. But in order to characterize it, I need to drive it through inverters, right? So that I can tell you exactly what the delays are. Yeah, any questions? This is clock and why? No, we need a negative latch here because I'm going to construct a positive edge triggered flop now. Okay, this is a negative latch. Okay, yeah. So I'm going to now put inverters here. Okay, and what do I do? I said put one more inverter here. Right, and this was my QM. Okay, so then I just copy this again. Okay, I'll place it here, and I'm going to now make the connection so that I can construct my flop. This has to now become a positive latch. So what are the changes I have to make here? Clock and clock bar. This will become clock bar. This will become clock. Right? And where should QM go? It should basically go to the D connection here. Right? Remember that you can do this wire or only at the output of a transmission gate. Okay? So clear? Now let's try to analyze what the setup, the hold time and the clock to Q delays are of this flop. Okay, so let us do the delay analysis. I want to calculate T setup, T hold, right, and TCQ. We will come to contamination and propagation delay later. Okay, let's not worry about that part now. Okay, I want to calculate these numbers. Now, in order to do this, we have to first make some assumptions on the clock edge. Okay, the first assumption we are going to make is assumption 1. Clock is ideal. What does this mean? Implies 0 rise and fall time. Okay, which means as opposed to what I drew earlier, the clock will now appear like this. Okay, so of course, if the clock edge is very fast, then because of capacitive coupling across this, that node can flip and all. Don't worry about that. We are assuming that those non-idealities don't exist at this point. Okay, capacitive coupling this way. Sorry. Okay, so we are assuming that the clock is ideal, and then we are going to do our analysis. Okay, how to do the characterization of setup, hold time, and clock to Q delay for a realistic scenario, I will discuss later. The simulation part I will discuss later. Okay, so this is my sampling edge. Okay, so let us now look at T setup. What is setup time? It is basically the time before the clock edge, right? When data should have stabilized in order to be sampled correctly. Okay, this is my clock, this is my D. The data switches from D1 to D2, and you want D2 to be captured, right? My Q should look like this. This should be D2, okay, with this delay. So what are we trying to do? We are trying to move this particular edge, T setup, closer and closer and closer, and then we are going to see when that data will not get captured. At what point will D2 not get captured? That's what we are going to theoretically first analyze. Okay, So for that, let me label these inverters I1, TG1, TG2, transmission gate 2, I2 and I3. Okay, this is let me call it, okay, I4, TG3, TG4, I5 and I6. Okay, I'm going to evaluate all these three quantities in terms of the delay of these gates, inverters and transmission gates. Okay. So now what happens? First of all, when the clock goes from 0 to 1, tell me what is the state of L1 in terms of whether it is transparent or opaque. Clock is going high. Sorry, L1 is opaque and L2 is transparent. Right? So in order for the change of D1 to D2 to be captured, some signals have to settle to the right value, so that when I cut this guy off, right, and make it opaque, when I cut the path to D and make L1 opaque, my latch should have captured the right value, and then it should hold it for the half cycle. That's the idea. Okay. So what do you think should happen? Like, for example, is the setup time just a delay of this inverter? Okay. Is it the delay of the inverter plus this transmission gate? TI1, TG1. So what should happen eventually? What is it that, what is the node that should settle to the right value? QM, right? This QM should sample D2 and should have settled to the correct value. When my clock edge instantaneously rises and shuts off this path, thereby turning on this guy, what are the gates that are going to drive QM? Yeah? I3, TG2, I1, I2, sorry, I2, right? So now, when my clock turns off and it turns on this feedback path, what you want to ensure is that the feedback path is holding the right value, right? Which means that if I can ensure that this capacitor here and this capacitor here are holding the same value. Remember, this is a theoretical thought experiment. Okay, practically it will be slightly different. We'll come to that. If these two capacitors are holding the same value, then when my transmission gate TG2 turns on, those two capacitors will charge share, right? And it will come to some value. Now, if both of them are the same value, then it's going to remain at that logic value. For example, if this stored a 0, okay, theoretically, and this stored a 1, then when my transmission gate TG2 turns on at the positive edge, just after the positive edge, this 1 and 0 will charge share, right? And now there is going to be a fighting between this 1 and 0, right? So if this guy is 1, how is he being held at 1? Which gate is doing it? I3. So there is a PMOS transistor driving this to 1. There is an NMOS transistor driving this to 0, right? Driving this to 0. These two will fight and come to some in-between value, which I don't know, right? It depends on the drive strength, it depends on noise, it depends on many things. So to be safe, if I can guarantee that both these capacitors have the same voltage, then I am sure that even after the transmission gate TG2 turns on, the voltage will not change, because there is no fighting now. Both of them are sort of the same thing, right? Oh, by the way, sorry, this guy is not being driven down. That's wrong. This is a capacitor on the gate, so that is sort of floating. I was wrong there. That's not being driven to ground, because that's an input of an inverter. It's a capacitor that's floating at ground. That means when this transmission gate TG2 turns on, and that has a logic 1 up there, that is going to charge this capacitor up now. Right? It's going to charge this capacitor. So this capacitor will start rising slowly. And instead of storing 0 or 1, it may come to some in-between value depending on where this voltage eventually settles, this node voltage X. If X is below the trip point of I2, then it will end up being a 0. If it's above the trip point, it will end up being a 1. So there is a sense of randomness there, which we don't want. Okay? What we want is both these capacitors to store the same value. How do I ensure that? What are the delays that are incurred in this process? I1, TG1, it has to go through I2 and also I3, right? Are you with me here? So what will happen? That setup time basically has to go through this path. This has to be my setup. This is an upper bound. If you ensure that by this time it settles, you are guaranteed that the correct data point will be sampled. Now in reality, the clocks may be non-ideal. It's not necessary that these two capacitors should always, land up at a voltage which is wrong. It may land up at the right voltage because it depends on the trip point of I2, right? So it may be fine. It depends on that feedback path and all that. So therefore, in reality, I'll tell you how to do this characterization. But what we are doing now is a theoretical experiment, thought experiment. And if you ensure that the data settles by this time, you are 100% guaranteed that the data will be captured correctly. Okay. So therefore, T setup, I am going to now call it, I am going to write it out as T of I1 plus T of TG1 plus TI2 plus TI3. Right? Now I'll ask you the next question. What is clock to Q delay? First of all, what is clock to Q delay defined as? After the clock goes high, how long does the data take to appear at the output Q? Right? So remember, by imposing a setup time constraint, we have ensured that the data has settled even in the intermediate node somewhere to some value, to the right value. So all we have to see is how long does it take for data to propagate from that intermediate node to the output correctly after the clock goes high. Remember, now the clock has gone high, which means L1 is opaque, L2 is transparent. Right? So what do you think will be the I4 plus TG3. Okay, so you're saying that this is that right? Now we don't have to worry about feedback path because this is L2 is transparent. We have nothing to worry about there. I ask you once more, are you sure this is correct? TG2. Yeah. No. But see, what we have done is, this guy had a voltage, input voltage. Across TG2 there was another voltage. Both are same. Now the feedback is switching, which means that the feedback loop had some value. Nothing is changing there. Huh? Sorry? That's the point. You don't need I4 because my signal has already propagated through I2. Remember, right? You see how the signal is coming. It's basically coming in like when it traces this path and comes here. By the time the signal goes all around like this, the signal would have also gone here. Therefore, I4 is not needed. Right? So let me take this off. I4 is not needed. So therefore, the clock to Q delay is only this much. So what is TCQ? It is TG3 plus I5. You need to be consistent about this. If you have said that the setup time is come all the way to I3, then obviously I4 will be out of the picture. Okay, you have to ensure this, because sometimes in some configurations, I am okay even if you say that the setup time does not include I3, let's say. Then in that case, your TCQ should include I4. You understand, ultimately the setup plus TCQ should take your data from input to output fully. That you have to ensure you are doing correctly. Because the reality is, both TCQ and T-setup are actually some numbers which are in between this total delay. If you add these two numbers, there is some sort of a constant that comes in. We will look at it later. Okay, so this is just a thought experiment, but please be consistent. Okay, any questions here? Yeah. Yeah, correct. That's the other thing. That's the assumption that I will write here. No clock skew. Absolutely. Which means the moment clock is going high, clock bar will go low. That's the assumption. In reality, it's not true. There will be a slight delay because either you are generating clock and clock bar separately and then doing a distribution, or you locally generate clock bar, which means again there's going to be a delay. Right? So this is also an assumption. Clear? Right. What about hold time? Now what is hold time? Right? Let's say my D2 changed here. Okay. I want D2 to be captured. That's my aim. Right? D2 changed before the clock edge and it changed after the clock edge as well, the sampling edge. But I want D2 to be captured and retained at the output through the entire time period. In order for that to happen, I should ensure that even if D2 changes after the clock edge, it is still captured appropriately if it changes after some time. Right? So for example, if I bring this edge very close here, then I cannot guarantee that D2 will be captured. In reality, theoretically we will see. So now again tell me what is going to happen when my clock goes high, and how do you think a change in D2 cannot, just slip inside and get into QM? Because if the change goes into QM, then I can't be guaranteed that the feedback loop will not capture that value. There is some randomness. Because remember, after that, L2 is becoming transparent. So whatever is at QM will just go through, depending on the feedback loop, of course. There is that constraint. but I cannot guarantee anything once because there is some randomness there. So clock is shutting off my TG1, turning on TG2. What do you think the hold time is? How long should I hold my data? Yeah. So what is hold time? Hold time is, definition is, data is clock, right? D. I cause a change in data before and after the edge. D1, D2, D3. The point now is, before the edge, when the change happens, I want that change to be captured. That is setup time. The change that is happening after the sampling edge, I don't want the edge to be captured. I want that to miss. I want it to retain D2 all through, right? So the point is, this change is T hold. Okay, in the sense, if it changes far away from the edge, then D2 will be captured, there's no problem. The change to D3 will be ignored. If you bring it very close, that minimum time after the clock edge where a change in D will not go through is defined as the hold time. Okay, so that's what I am trying to analyze here, again under these theoretical conditions, under the assumptions we have made. So if my clock edge first of all changes, let's say, and B changes after that, what is the minimum time that D needs to even arrive at the transmission gate? I1, right? So if my clock shuts off at 0, then actually there is one inverter to further delay the change in D, right? So actually the whole time is negative. D can change immediately after the clock edge under these theoretical assumptions that you have made. Clock is instantaneous, no skew and all that. The moment you introduce skew, you will see there's a problem. We'll look at that later. But right now there is negative hold time, or safely you can define this as 0.